Exercise 9.5. We suspect that the flies in our house are larger than normal. So you look up online the lengths of flies and you find that they're normally distributed with mu equal to 6.3 millimeters. You catch 7 flies and measure their lengths, and here are the lengths that you see. So now our goal is to create a hypothesis test and go through that hypothesis test and determine are our flies larger than normal, or are our flies not very different from the same size. Okay, so so what we need to do is we need to follow those same steps that we're always following. So let's start with our hypotheses. So our hypotheses, we've got our null and alternative hypothesis. If our flies are the same as every other fly in the world, then we would expect the average to be 6.3, because what we see is that because what we see is that we're given this default average of 6.3. So if there's nothing different, our flies have an average of 6.3. So that's our null hypothesis. What's our alternative hypothesis? Our alternative hypothesis is that flies are actually bigger than 6.3 inches, because we believe that our flies are larger than normal. So this is normal. We want to do the alternative hypothesis that our flies are bigger than normal. I don't like my greater than. Let's rewrite it. Okay, so here's our null and our alternative hypothesis. You can see already that this is going to be one-tailed. And we can see from this that it's going to be a right-tailed problem. And we can also see that that we're in the case where sigma is unknown. So sigma is unknown because our problem doesn't tell us what it is. So we can see right away that we're going to need to use a t-distribution. So we're going to be in a situation where we're using a t-distribution. We're in a right-tailed test. Okay, so now let's go and let's start attacking this problem. So our next step is to find our test statistic. But before we can find our test statistic, we need to know what is the average and what's the standard deviation for these values. So we can do that. The way I would do that, you could do it by hand, but if I were you, I would choose to not do it by hand. I would use my calculator. So I'm going to go to the Stat button, and I'm going to go to Edit, and then I'm going to enter all those values in L1. I had already entered them because we did this problem before. And then I'm going to quit out. I'm going to go back to Stat and Calc and go to one variable statistics, hit Enter, and there we go. Make sure that if you have some other data that you're pointing to the right place. So now that I look here, I get my average, which is 6.54 for my X bar. Here, let's write X bar equals 6.54, and S is my next number, and my S number was 0.5798. So let's just do 0.58 for S. Okay, so there's my X bar and there's my S. Okay, so I'm ready now to start tackling the problem because I have my basic data that I need. So as I start tackling my problem, I'm going to find my test statistic. And my test statistic, remember I'm using a t-test statistic because we don't know what sigma is. Our problem doesn't tell that to us. So that means we do X bar minus mu divided by S over the square root of n. And now all I have to do is go pick the correct values for that. So let's come over here and let's pick all of those. And so X bar is my average. X bar is my average from my sample. So X bar is 6.54. Mu is always from the null hypothesis. So mu is going to be this 6.3 that we started the whole problem with. 6.3 divided by S, which is 0.58 divided by the square root of n. And in this case, n is how many? So I just come over here and I count. 1, 2, 3, 4, 5, 6, 7. And so n is 7. And so I put 7 on here. And now I have to type all this in my calculator. Just like last time, be very careful as you type these in. Make sure that you follow the order of operations. It's easy to get it out of order. So I'm going to do I'll just type it in all at the same time. 6.54 minus 6.3, close parentheses, divided by open parentheses, 0.58 divided by the square root of 7. Close those parentheses and hit enter, and I got 1.09 for my answer. Oh, let's put a 5, 1.095. So here's my t-distribution. So now that I have my t-distribution, I'm ready to find my p-value. I'm going to always draw a distribution every time. Normal distributions and t-distributions look the same. It's just t-distributions are more spread out. So I'm going to draw the same picture every time. And now I'm going to put that t, 1.09 on here. 1.095. And now what is the p-value I'm looking for? Well, notice I'm at a right-tailed. I have a greater than sign. So that means I'm going to shade the right-hand side of this thing. And so my p-value is that section that's over on the right-hand side of 1.09. So I'm going to use normal CDF. I'm going to use normal CDF. I'm going to have my lower is going to be 1.095. My upper is just any really big number you like. I'll just put a bunch of 9s on there. And then remember, we always use mu equals 0 and sigma equal to 1. So I put all that on there to get my result, and I'll come over here and go distributions. Oh, wait, hold on. I just messed that whole thing up. I don't want normal CDF. I want TCDF. What was I thinking? How do I know I want TCDF and not normal CDF? Well, it's because I'm working with a T distribution, right? So come on, Brian, pay attention. Okay, so TCDF, there's our lower and there's our upper. We don't have to tell it mu and sigma, but we do have to tell it the degrees of freedom. And the degrees of freedom is always 1 minus the number. We had 7 flies, so that means our degrees of freedom is 6. So now 7, and 6. Okay, so now let's come and do that. Now, TCDF is what I want. So there's my TCDF. Hit enter. And then you all will have a menu, but I'm just going to type it in. 1.095, comma 9999, comma 6, and hit enter. And I got 0.1577 as my answer. 0.1578. That sounds decent. Okay, so that's my result. So that's what I got for P. And so the one last thing to do in my problem is to try to draw some sort of conclusion. So what's my conclusion? Well, I'm using alpha equal to 0.05. And so what I have to do is I have to compare 0.05 to 0.785. And which one's bigger? The 1.5785. So 0.1578 is bigger than the 0.05. So that means that P is bigger than alpha. So what's my conclusion? Do I reject H naught? Do I fail to reject H naught? What we should think about is very small alpha values means that we proved what we wanted to prove. So small alpha values are good, and good means we reject H naught. Anyway, so small, I'm talking gibberish. Small p values, so if p is really, really small, that means that our null hypothesis was really, really, really unlikely, and so that means we reject H naught. This is a big alpha value. Big alpha values means that our null hypothesis was a reasonable hypothesis, and so we fail to reject H naught. So p is greater than alpha, we fail to reject H naught. What does that mean in practical terms about our flies? That means that we do not have evidence that our flies are larger than normal. So we were hoping that our flies were larger than normal. We really thought so because they were causing a nuisance and they seemed really big. But after doing a study, we don't have evidence our flies are larger than normal. Now, when it comes to research, you could gather more flies. So maybe if we'd gathered 50 flies instead of 7, we would have gotten a different result, and maybe then we might be able to draw a conclusion. But at this point, with these 7 flies, we can't draw any conclusion their flies are any different than normal. All right, now it's time to try exercise 9.6, and I'll see you there.